Hello there. Welcome to my project assigned by Sky-Fi Labs on machine learning using Python, and this project is based on linear regression. I would like to briefly introduce about this project. Using the Boston House dataset, which is already there in the sklearn's dataset library, we are going to model a price predictor using linear regression technique. A Jupyter Notebook is used as a programming tool, which is a web interface for Python or R programming languages. Easy to read text with code blocks. Let's start by importing some important Python modules or libraries. NumPy or numerical Python, which is a math library for Python, it deals with multi-dimensional arrays as a data type. It includes high-level mathematical functions and array operation. Here we will be using it for vectorized operations. Pandas is a Python library to handle large datasets. It provides data structures and built-in functions to handle data operations. Also used for reading and writing data from and to spreadsheets, in general the CSV files. Here we will be using it for creating and handling Boston data frames, that is features and target. Matplotlib is used for plotting operation. Easy to generate a variety of graphs. We will be using PyPlot and Func animation for plotting graphs and playing animations. Scikit-learn is a Python-based machine learning library which consists of libraries for supervised and unsupervised machine learning algorithms. Easy to implement ML pipelines as all the required functions are inbuilt. Some specific modules like dataset of Boston house price, mean squared error, train test split, and min-max scaler, which we will be utilizing here for simplified learning. Also we will be required of importing HTML from ipython.display for showing the videos. Now let's see the steps involved in solving a problem with machine learning techniques. The first step is data processing or data cleaning. Second, we define error or the loss function. Then we split the data into training data and testing data. Then we need to train the model. This step involves learning the target function from the given training data, choosing the appropriate machine learning algorithm, and then we obtain the predicted value for the given input and visualize the result in the final step, that is prediction. The problem statement is to predict the price of house, but in order to train the model to predict the price of the house, the model has to look at the data and learn the relationship between the features and the price. We will use the Boston house dataset for this purpose. So let's begin with the first step, that is data pre-processing. Load the dataset with load Boston and store it in a variable named Boston. To obtain that Boston description, we use the Boston descriptor. This description is provided by a sklearn library. The Boston house dataset consists of 506 data points, 13 features and 1 target. It is important that we understand what each of the columns consists, so that we can choose only the relevant attribute to predict the price of the house. Now to perform or use these data, we need to create a data frame object, let's say features. We can perform various operations on pandas data frame, for example selecting any column. Now we need the target data frame which will hold the price data. We define the data frame object named target. The data frame takes 2 parameters, Boston.target and the column name. We name the column as target. Let's print the maximum and minimum values of the target. Now let's concatenate the features and the target into a single data frame using the concat method. Since we need to concat column wise, so we set the axis equal to 1. By default, the value of axis is 0, so this will add the two columns or two data frames row-wise. We use the describe method to generate the summary of the dataset. We want to know which of the features can be used to best predict the target variable. There are multiple techniques available to implement this. We will do this by statistical technique called correlation. Correlation describes how closely the values in one column are dependent on the values of the other column. Let's say for two columns, x as independent and y as dependent. The positive correlation means as the value of x increases, there is also increase in y. The negative correlation means as the value of x increases, the value of y decreases, and vice versa. Whichever attribute has the highest absolute correlation with the target, we will choose that attribute as the independent variable to perform linear regression. Point to be noted here is that the correlation is not always the causation. To compute the correlation, pandas provide a method called cor. It returns the data frame and contains the coefficient of correlation between each parallel attributes. The method we choose here is the Carl-Pearson method. Using the list comprehension, we extract the absolute values of correlation. We obtain the list of pairs of correlation and features using zip function, which takes multiple lists and returns tuple of correlation and features pairs. Sort the list of pairs in descending order. We observe LStat has the highest value of correlation. Now we separate the correlation values and labels into separate lists. Now we are left with the task of plotting a bar graph for more clear visualization. The bar function takes the parameter index, which is array of number of bars. List of correlation values, which acts as the height of bar, and width, which specifies the width of the bar. The axis of x is labeled as attributes and the y-axis as correlation with the target value. X-tix is used to label the bars with the name of the attributes. Our next step is to prepare the data for a linear regression. Let's first select the column we are going to use as x and y. X contains the values of LStat column and y contains the values of target column. Now we perform normalization on the selected column. The goal of normalization is to change the values such that after normalization all the values lie in a common scale. In our case it will be between 0 to 1. So the interpretation of data becomes easy. Let's print few values before normalization. As we can observe, they are in arbitrary range. A sklearn provides min-max scalar that takes list of values in any arbitrary range and gives a list in which values are in range 0 to 1. The fit transform function computes the minimum and maximum, transforms the values and returns the normalized value. It expects the values column-wise, therefore we shape the values with numpy function reshape to have the shape n rows and 1 column. No need to have prior knowledge about rows. We can pass -1. The correct values will be automatically used for that dimension. Get the normalized values stored in X. Similarly, we reshape the target values. Now if we print the values, first values, we find that they are in range 0 to 1. In machine learning, the data used to build the final model comes from various datasets. In particular, 3 datasets are commonly used in the creation of model: training, validation, and test datasets. The model is initially fed into the training dataset, training used as a supervised learning method. Test dataset is used to provide an unbiased evaluation of final model fed on the training dataset. It is only used once the model is completely trained using the training and validation sets. It is not feasible to manually provide a large number of samples to test the model. Therefore, we use some samples from the dataset for this purpose. This part of data is called the testing data. We do this by randomly choosing some percentage of sample from the dataset and exclude them from the data shown to the model during the training phase. The part of dataset the model used to see during the training phase is called a training dataset. sklearn provides a function train test split. The parameters are the datasets and the fraction of the dataset to be considered for the test data. The dataset is given in two parts, the features and the target. The function will return 4 return values. We now have the training dataset that we can use to train the model and testing dataset to evaluate the model.
Gradient descent is an optimization algorithm to minimize a function. In multiple step moves in a direction of steepest descent, which is the largest negative gradient. These iterative steps can be too low or too high, and the cost function is to be minimized. The purpose of update function is to calculate gradient at current position. It updates and returns the value of m and c, taking the parameters slope or weight m, intercept c, attribute values x, target values t, and learning rate. We compute the gradient using the formula using numpy vectorized operation. We multiply the gradient by learning rate. The learning rate controls how much the weight changes. The error function calculate the cost function at current position. It takes parameters m, c, x, and t. This function returns the error value. To compute the error, we first store the size of the attribute values, then we use the equation to compute the error and return it. The gradient descent function is used to implement the gradient descent algorithm with the help of two functions we defined earlier. First, initialize the m and c variables, the error values, in the mc values list. Then enter a loop until the number of iterations is reached. Compute and store the current values of weight. Check if error has gone below the threshold. If the error is less than threshold, then break from the loop and stop further training. Append the error to the array error values. Update the weights using the update function. Append the update weights to the list mc value. After coming out of the loop, return the final values of the slope m, intercept c, error values, and the mc values. Now we set the initialized values of slope m and c equal to 0, setting the learning rate below 0.0025 so as it don't cause overflow in weight values. Set the number of iterations and set the threshold. Finally, we call the gradient descent function. This function may take few seconds to execute. So to record the time taken for the execution of the cell, we use magic function timeite.
Matplotlib provides a class called funcAnimation to generate animation of graph. We will use this class to generate the animation of the regression line changing from the initial position to the final position. In order to use this class, we first need to initialize the variables. Generating animation is a CPU intensive task, so we limit the number of m and c values by selecting the value at specific intervals, let's say every fifth value. Call the function subplot. It returns figure and axis object. Then initialize the line object by calling the function plot with empty arrays for x and y coordinates. Set the animated to be true to indicate that this line to be drawn is animated. Generating the animation requires two functions, so we define the init and update function. The purpose of init function is to initialize the graph. We will draw the data set using a scatter plot and set the limits of x and y axis. This function doesn't take any parameter and returns the line object. The update function is used to set the data for the next frame. In our case, we use the function to extract the next slope and intercept values
from the array of MC values and compute the coordinates of the endpoints of the regression line using the line equation and set them using set data. This function takes one parameter as frame number used as the index of the MC values, extract the M and C values using the frame number. Now we can instantiate the func animation object, and then we can generate video of the animation that can be shown in the Jupyter notebook using HTML5 video and pass the return values to the HTML function. We see the animation of linear regression line shifting starting from the initial position to the final position. We can see the line is becoming more accurate with each iteration. Let's plot the regression line on the training data that is represented as a scatter, showing how the training data is distributed. Next we plot the regression line. We already have the x values, that is x train, and the predicted value predicted y value is given by the line equation using the final slope m and the intercept c. We can observe that the training data doesn't lie on the straight line, having a slight curve, and the line that model predicted is a good approximation of target values, as the line lies at the center of the dense part of the training data. There are also some outliers for which predicted result may not be very accurate. Next we plot the error values using the error value list that we obtained from the gradient descent function. If we plot these error values corresponding to each iteration, we will get a plot that will show us how the error values changes as the training progress. The label for x-axis is iterations and y-axis is error. We can see in the plot that error values are decreasing with each iterations, which is as expected. After a certain iteration, the curve is almost parallel to the x-axis. Now we are at the final step of prediction. We first generate a list of prediction values using the line equation. Let's call this variable as predicted. Next we compute the error using the mean squared error method provided by the scalar library. The parameters to the function are target values and the predicted values. We observe that the mean squared value is quite low. Next we construct a data frame having x test and y test and the predicted values so that we can compare the values. We can observe that the predicted values are quite close to the target values. We will now plot the predicted values on the top of the target values. We will plot a scatter plot of the testing data colored in blue. Then we plot the predicted values whose color is set as red. We can observe that the line is oriented in the same direction as the testing data. These are in terms of normalized value. We need the predictions in terms of the price as it is in the original representation of the dataset. To do this, we use the inverse transformation function in the min-max scalar object. First, we must reshape the data to confirm the shape required by the scalar, that is, in vertical orientation. We do this using reshape function. If we use -1, the correct dimension is automatically computed at the runtime. We do this for predicted x test and y test arrays. When the data gets scaled back, an extra dimension gets added to the data. We remove the extra dimension by a slicing operation, as select all rows represented as the colon and extract the last element of each row represented by -1. Now we use inverse transformation to obtain data in original scale. The parameter to this function is the data to be scaled. Now we can construct the data frame having predicted price and the actual price side by side. Now we are going to train model with different attributes and predict. We will observe how regression line changes if we consider a different attribute as independent variable. We have learned that choosing the attribute with highest correlation will give the best prediction of the target variable. Now we choose some other attributes and observe how learn weights and error changes. Let's choose RM and observe the differences in the result. If we observe the mean squared error corresponding to the RM attribute, we find that it is approximately twice than that of LSTATs. Now let us choose the attribute with the lower correlation with the target attribute. Let's select DIS and see the results. We can observe in the scatter plot that the data is scattered all across the graph and doesn't lie along a line. And so there is a high mean squared error value which is approximately 4 times than that of LSTAT. Therefore, the assertion that we have to choose the attribute with the highest correlation with the target value or target attribute turns true. So that was all about this project. Thanks for watching. Happy learning.